I'm pretty sad. It's okay.
Yes.
No.
Okay. So the question again, and this is for the benefit of the folks at home. List and explain Newton's 3 laws of motion. First law, object at rest stays at rest, or if it's in motion, it stays in motion. Second law, force equals mass times acceleration. And third law, if you've got 2 objects that are interacting, they exert equal and opposite forces on each other. The end. On to our notes today. So, a lot of the notes you probably don't have to write down, which is good because then I don't have to write them down either. So I'm just going to put some of this stuff up on the screen for you. It should be pretty much review from last year.
Tell them Mr. Hathaway.
Or whenever you take regular physics.
Yeah, you tell them.
Right.
Wait, so is this going to be like an easy unit?
Depends on how much you enjoyed force diagrams.
Oh, I like them.
It took me a while to get used to
It's
them,
like a
but I
solid
understood them.
stretch.
I really liked them the last week.
It's gonna be a no for
Yeah, I
me.
like
Almost to the point where it's kind of weird.
And I genuinely get excited when we do that.
So you guys like force diagrams?
No.
Okay.
I like force
I don't like
diagrams.
anything.
All right. I like how the picture of me up here is like a little bit behind the picture up there.
Yeah, the leg. Do you ever watch those, like the TV shows that have like the TV inside the TV and the TV? Or
Yeah.
like the snow globe where there's a snow globe inside the snow globe inside. That's a concept that always fascinates me.
Right.
Okay, well,
We deal with that every day in physics.
In a simulation that's being run by a simulation.
Yeah.
This is not the class for this. My head's already like gone.
Okay.
Just ignore us until we say, Kylie, pay attention.
What if
You
someone
could probably,
creates a
like,
simulation
high-five
that creates a
yourself.
simulation?
Yeah, probably.
Yeah, help. You have to go to the.
Oh no!
What if someone creates an AI that creates an AI?
Can I
I mean,
hit myself in the face? Hang on. I gotta. Nope.
I mean, like,
Ah,
You have to
fail.
pretend to be hit so everybody like does that too.
Right, right.
Because there's a little bit of lag, but actually.
I want you to go like all the way to the right edge of the screen and give a high five and move fast enough to reach the lag.
So I have to go.
what if it's weak on?
Right. Okay. I got this. Here we go. Oh no!
Mr. Hathaway!
Okay.
Are you okay?
Good to go.
What causes this?
That's such a.
We're talking about force. Someone save Sarah.
I forgot the stairs were there.
Like the real one?
Hi, Clint.
I think the moon's a Saturn.
Moon's a Saturn?
Wait, are there real ones?
No,
Are you looking for the.
it's a secret. Are you for real?
There you go.
This is the AP physics.
I
Yes,
myself
it's our
am
AP
the
physics
biggest.
course.
It was one day.
Have a
Hannah
good
gave
day.
me fruit snacks that were in the shape of vehicles.
Okay.
Yesterday!
So, what class is this again? AP
I
Physics.
don't know.
So, laws of motion.
Astronomy. No, it's
You would have wished this was astronomy. We talked about Uranus the last couple days. Okay. And you would be shocked at how little reaction I got from that unit. Like I try and push the envelope a little bit, getting people to laugh and giggle, and no one did anything.
Really?
Everybody held it together. The very
I'm
first
disappointed
slide,
with Hannah.
not even Jeff. Everyone, get out of this.
like the very first slide, was about a probe going in to Uranus, and nothing. Dead silence.
I really like that this is shown up in 2 videos that aren't astronomy.
I wonder what you folks at home think about this here today. We are not wasting time, I guarantee. This all has a purpose.
I really hope you found that we can skip ahead most of the time in these classes. Thank you for your time.
All right.
I'm gonna leave.
So, force is a push or a pull,
I'm so
and these are vectors, which means you have to take their directions into account. Now, if we have a net force that is not equal to 0, and what this symbol means is it means the sum of all of our forces. I'm going to be using that because it's easier than You know, you kind of got to get used to this, especially if you're going to go into math or calculus, because you use this often. The sum of all the forces is what that means. It's equivalent to net force. If that's not equal to 0, your motion's going to change. You'll either pick up speed, or slow down, something like that. If the sum of all your forces is equal to 0, then the motion will not change. A little bit about field forces versus contact forces. Gravity, electric fields, magnetic fields. These are forces that act at a distance. Yes?
Your sigma kind of looks like a two triangle symbols on top of each
I
other.
thought it was a less than with like the line
Yeah.
where you go to, but then I realized it was connected.
It also kind of looks like the side of a Christmas tree, doesn't it?
Yeah,
Is
but
that
what's,
a V?
what's the symbol? What's the symbol?
That's summation.
That's a-
With the other one, I want you to draw the head of a bird so that it's the beak.
Oh, sure.
We don't waste time making physics.
No,
That
wait, what's...
bird. It looks
Okay,
like it's
okay,
crying.
Add it here.
The F is the tier.
What's the symbol?
Maybe we should just start
What's
over
what?
with this recording.
What's this supposed to-
This?
Yes.
It's a Greek letter, capital sigma.
Sigma. It's
Yep.
Summation.
Lots of times it has little.
If I draw it carefully, it looks kind of like this.
And
Or-
yours has a little end cap.
I think it's supposed to be level on the top and the bottom.
And it has like a little end cap.
Yeah,
It has a little look into it too.
yeah. So anyway, it means the sum of.
That was a really sad end cap.
You're halfway through the joke.
Of course I like jokes.
I got one.
Oh boy.
Okay.
How about we have it at
Let's-
the end of the class?
Yeah, let's do it at the end. I want to make sure we get as far as we
So
can
actually
today.
got through this.
I think we will. I think we will. Contact forces, these are forces that occur because things are touching, whether it's a normal force from the ground, an applied force, which is by a push, a tension force, which is by a pull, or friction. With me so far?
Kind of.
Newton's first law. Motion doesn't change unless you have an unbalanced force acting on it. In other words, your net force would have to be equal to something other than 0. No change in velocity if the sum of all your forces is equal to nothing. If you do have a net force, then you will have a change in velocity. I don't think I need you to write that down. No,
Okay.
you don't have to write any of this down. I don't think. If it sounds not familiar, then you might want to. A little bit about mass. Mass we measure in kilograms. Weight is measured in newtons. The unit on newtons is kilogram meters per second squared. You can think of it as, F equals ma. Mass is kilograms. Acceleration is meters per second squared. So it's just a combination of those two things. If something is asking for the weight of an object, the weight is equal to force of gravity, except it's not negative. So your weight is equal to force of gravity negative, the opposite of that. So if your force of gravity is negative 200, your weight is 200 newtons. Newton's second law of motion, F equals ma. We'll be spending a lot of time on this, and most of the notes for today is going to be on one particular example that we'll get to at the end. But F equals ma, and this plays into Newton's third law, and I used this analogy last year of when you have a fly flying into your windshield and you're on the highway. You don't notice any change in speed, even though you're undergoing a very, very tiny amount. So in terms of the car, this would be that force. Big mass, tiny acceleration, you can hardly tell that your car is changing speed at all. So that's equal to some sort of force. But the fly, which has a tiny, tiny mass, is undergoing a massive acceleration, and that ratio and this ratio are going to be the same. So you have the same force in both cases, even though it seems like the fly is undergoing a much larger force than the car. But in the end, they're the same from Newton's third law. As far as Newton's second law goes, net force equals ma, and this is kind of the equation that you need to know for this section. F equals ma. Your overall net force in any direction must equal mass times acceleration. And this goes for the x, y, and z directions as well. Newton's third law. I'm just going to let you read this. Take about 30 seconds. Yeah.
Remember my example from last year that I put in my presentation?
No, what was it?
That was the meme where it's like Isaac Newton's left roof, the roof of the car, and the roof of the car stopped Isaac Newton. Nice. Remember
I
that?
forgot about that one.
Yeah, you gotta remember that one. Apple and
So yeah, Newton's third law has to do with the forces that objects experience because they're touching each other. If two objects are pushing against each other in one way or another, or are just in contact, those two forces are the same. So if I'm pushing this table with 100 newtons and it's moving, it is pushing back with 100 newtons. If I push on it and it is not moving, it's still pushing back on me with the same force I'm pushing on it. No matter what, those two forces will always be the same. You need two objects for Newton's third law to be true. And this just says, you know, the force of object 1 on 2 will be equal to the negative force of object 2 on 1. Alright, now we're on to the stuff where you can actually take notes. And we should have plenty of time to get through this. This is going to be a fun ride.
Okay, girls, let's go.
So, tension. When an object is moving and it's being pulled or being pushed,
With a stone.
we have to make sure that we know the definition of both of those. Applied force is when you're pushing it. Tension force is when you're pulling it. If you remember that, you don't need to write that down or make a note of it, but just make sure you're aware. Applied force is push, tension force is a pull. Here's a question for you.
What's 9 plus 10?
I wish.
It's 1.
21. I don't know, if you can make that into a really cute
200.
robot.
Look. Oh. Wow, someone.
How much tension is in the string? It's in newtons, so this isn't mass. You don't have to do anything with 9.8. Oh my gosh.
Those are some stubborn stains.
Yeah.
Maybe if you had oxygen, they'd go right away. Shut up.
So what do you think the tension in the string is?
I think it's 20 newtons. I think it's 2 newtons, but you know, I'm wrong. I think it's
10? I'm hearing 10 and I'm hearing 20. And the answer to this is 10.
10.
And the reason that it's 10, because it's real, you know, your gut kind of says, well, we're pulling 10 down here and 10 down here. But the trick with a lot of these force problems is you have to isolate them. And if this mass is not accelerating down, if it's going to be holding still like it has to, because it's the same weight on both sides, then the force going down must equal the force going up. And if you've got 10 newtons going down, you're going to have a tension force going up of 10 newtons. Another way to think of this is, you know, it's holding still, so maybe we just get rid of this side and we put a wall here. So it's going to be 10 newtons, whether you have a mass on the other end or whether it's connected to a solid wall. Now, in terms of numbers, maybe we've got a hanging mass of 7 kilograms, and we want to figure out what that tension is going to be. This will probably be the most basic force equation that you get in this chapter.
I got you, Mr. Half.
Tension minus gravity equals mass times acceleration. And in this case, this object is hanging from a ceiling. It's not accelerating anywhere. So acceleration is equal to 0. So your tension will be equal to your force of gravity, which is 7 times 9.8.
68.6.
Yes.
And that is on
There we go. So that's your tension there. How are we doing so far? Okay. So again, all you're doing for force equations is you're doing the force in one direction minus the force in the other direction, and setting that equal to either ma or 0, which you could set this equal to 0 right off the bat, because you can tell that it's not going anywhere.
So the tension is going
Why it's not
upwards of
negative?
7 and the gravity is going down at 9.8. So that's where you have the number.
Yes. Because force of gravity is always mass times 9.8. Yep. All right. I think 15 minutes should be enough to go through the long example. And that leaves about 4 minutes to do this next thing. I'm going to go to the store and get better rags, because this is
You
insane.
can do that in 4 minutes.
Well, he does have the good whip in the back.
I don't know. Maybe
If-
that's, you never told us where that staircase goes.
No,
Oh, it goes to my treadmill, which I train on regularly. So yes, I'm fast enough.
Oh, I thought you were going to say your
I love how it
interdimensional.
doesn't go to the store. It just goes to the treadmill.
Yeah, I go to the treadmill. What's your excuse?
So, yeah, friction. We got to talk about friction. If you've got an object on a table, going down is gravity. Going this way maybe is tension, or you could say your applied force. What's going up?
Normal force.
Normal force. And going the opposite direction would be your friction. So that's F with the little mu next to it. Some people like to put a little F. You can do that. That's totally fine.
The little left.
Well, or it's not static friction, right? It's just
Right. If it's moving, it's regular friction, like what I have here. If it's holding still and it's not budging, then it would be static friction. You can write that as well. So this is for if an object is sitting at rest on a horizontal surface, you're not pulling up, you're not pushing down, your normal force up will be equal to your force of gravity. And FGY, this is something that comes into play when things are on an angle, that will be the same as those in here. But you're not necessarily going to be labeling anything.
horizontal surface.
Yeah, yeah.
Well, why there's like angle?
If it's on a slant.
Yeah, if it's on a slant,
But
then
that
you'll
way
be...
not
And the reason I'm inserting it right here is because I got 3 of these that I'm going to use. And I just wanted to have them all the same everywhere. So, if you are on an inclined surface, then you've got normal force being equal to FGY. However, the force of gravity that you have in the y direction is not going to be equal to your force of gravity. Because when you're on that angle, your force of gravity is not exactly in line with your y-axis. If you remember a little bit, we have to rotate our x and y axes under those conditions. And we'll practice that tomorrow. Yep.
I have no idea.
That's for free falling.
And so this is the last scenario. If you're on a horizontal surface and someone's pulling up or pushing down on that mass, under those conditions, your normal force will not be equal to your force of gravity in the y direction. But under those conditions, your normal force will be equal to, it will not be equal to either of these, I should say. But anyway, all this stuff right here, you'll see examples of. I just kind of wanted to put it out there so that when we do these examples, you can kind of look at this and see where it's coming from here. So don't think too much about these right now. Yes?
How did you get through this without Miss Kitten, like, saying W/forces?
What?
What?
Miss Kitten really, really gets mad when you say, like, W/ or other, like,
Oh.
things.
Because this means with? She
Yeah.
doesn't like that?
How did you get through this without Miss Kit?
What are you talking
about?
When did she?
She said that to me in, like, or, like, no, to the entire class.
But we're in physics. What are you talking about?
She's in California now.
I'm confused.
I'm wondering what type of assignment it is.
Okay, but if you're from California, do you even exist?
Yeah, that's it.
What?
Yeah.
Okay. 15 minutes. Let's see if we can do this here.
Do what? I don't think I'm ready.
Oh.
Trying to think in terms of the best spot for this.
Mr. Hanford,
Yes.
which side of the chicken has more feathers?
Left side.
Yeah, I'd go with Placido.
The outside.
Well, it is the
I
left
was gonna
side.
say the lives. Because then you
Right. What do you have against dead chicken?
feather it.
Is that a wine?
Stoplight.
Is that a wine glass?
Sure
On top of
is.
a Stoplight?
A wine glass on
No, it's a
top of it.
martini on top of the
It
side.
looks like a hanger.
So this is a little stoplight here. And
Not all about it.
you gotta put some colors in here.
Yes.
Yeah, you do. I think it's red. I think we need to
I
stop.
have yellow and orange.
What
What do you need?
Why do you need orange?
For the yellow?
Yeah. Oh, like for the.
For the yellow?
No, don't do it! I have yellow and
You do have yellow?
Yellow and orange. Which one?
Give me orange. That'll show up better. Thank you.
It's a dry erase marker.
There we go. Thanks. Okay, so we got our stoplight here. And there's a lot that we want to figure out about this stoplight. It's very special. We got a 37-degree angle right here. We've got a 53-degree angle right there. Moreover, we know that the mass of this stoplight is equal to 15 kilograms. And this is a physics problem if I've ever seen it.
Yeah, I was gonna say, this is
I
a very
feel like this
unrealistic
is what
example.
you do at long stoplights.
We
He's like, oh no, they figured me
That's
out.
a good one. I like that. We actually call this static equilibrium.
That's all.
But you wanna do that? Is it because it's like that force equals 0?
Yes. Static equilibrium is the forces when an object is holding still. And we want to figure out all of these forces before the end of the school day.
No. That's not possible.
FT3 is there. FT1 is right here.
Oh, you said we needed 15 minutes. You don't have to. Wait till tomorrow.
And FT2 is right there. We want to figure all three of these out.
What is a virtual student's gonna do?
So, let's see if we can figure this out here. FT3 should be pretty easy because, yeah, your force diagram would be tension 3 up minus gravity down, and the force equation would be FT3 minus FG equals 0 because it's holding still. Therefore, as you probably wanted me to say right from the beginning, FT3 is equal to the force of gravity of the whole object. So force of gravity is mass times 9.8.
I don't know the answer.
What's that?
I mean, you
So 140 something.
Is that what the calculator says?
It's
140 something?
That's
Yeah,
what
it does say 147.
147.
147 newtons. Hey, we're a third of the way there. Woohoo! Okay, now we got to figure out the other two. And this is where things get a little bit tricky.
Oh, could you
So-
make, oh wait, is FT3 also equal to the height of that triangle?
No. Well,
Of course.
not in terms of length. but it does play a part that we can use. So first thing you might want to do for a problem like this is redraw it, because this looks complicated.
You gotta redraw that card.
So I just draw it so we've got FT3 at the bottom. FT2 is going up like this. And FT3 is going over like that.
Oh, you can do that is the F.
Wait, you have two FTs.
I do not. Goodness. See?
I don't know what happens. You just magically change.
So here's a little bit of math. If this is 53 degrees up here, like if I had a line there, what's this angle?
That'd be 53.
Exactly.
Never mind. I failed geometry.
It's okay.
If this is 37, like here, what's that?
37.
Very good.
Woo,
So we
nice.
have ourselves a force diagram. What you have to do every time you're dealing with a super complicated looking stoplight problem
Sine, cosine, tangent.
or other problems like this, all you got to do is divide it up into its x and y components and see where it leads you. So let's take a look at the x direction. Okay? In the x direction, what forces do we have? We've got FT2 partially going to the right. So sum of all the forces in the x direction. FT2x minus FT1x. Hi there. And that's going to be equal to 0 because it's not going anywhere. And I might want to just make this a little bit more specific. Perfect. Okay.
Astronomy.
Thank you so much. So, let's be more specific with this now. This side, the x component, is going to be what? Sine or cosine?
That's cosine.
Cosine, because cosine takes the adjacent side into account. So FT2x, another way of writing that is just FT2 times the cosine of 53 degrees. And you would get that because cosine of 53 is equal to adjacent over hypotenuse. And if you isolate the adjacent side, this is the equation you come up with. So, we have that equation minus FT1,
I thought it's
and that's cosine for the same reason, because it's going to the left. And that's equal to 0. And this is what's going on in the x direction. Questions so far? Okay. So now we got to look at what's going on in the y direction, because we can't go any further with this. We got one equation with two stupid unknowns. So let's see what's going on when we look up and down here. In the y direction, we've got, should I just skip to this level or should I do this?
Yeah, skip.
Okay. So in the y direction, it's the same story, but sine, because the opposite side is the vertical. So it's going to be FT2 sine 53, this might get a little long, plus FT1 sine 37 minus FT3, which is going down. We said that's 147. And after all that, you're going to be equal to 0. Yes. But we've still got two unknowns. So we're going to do a little bit of math to fix that. Forget what the rule is called, substitution or something. What I'm going to do is I'm going to take this equation in the x direction, and I'm going to go ahead and I'm going to solve it for FT2. And that's one way you could do it. You could also solve for FT1. So, yeah, systematic equations. What's it called? Just systematic equations?
system of equations.
Okay. So I'm going to go ahead and solve this for FT2. So this moves all the way over to the right. And then I want to divide both sides by cosine 53. and that gets rid of it over here. So FT2 is simply equal to tension 1 times that ratio. That ratio should come to 1.33. And this is an important number because it allows us to figure the rest of this out. So if I take that and I throw it into my equation, throw it in right there, then I have an equation that I can actually solve. Okay.
I tried to follow the lines you did, except mine don't look as good as yours.
So if FT2 is 1.33 times FT1, essentially what I'm going to be doing is eliminating one of the variables in this equation. So I'm rewriting this equation now. .33 FT1 sine 53 sine 37 minus 147 equals 0. That's one equation with one unknown. So the next step, I'm going to take the 147 and I'm going to chuck it over on the right side. I'm going to take my FTs and I'm going to pull them out, whatever math term that is. The opposite of distribute. I'm going to anti-distribute my FT1.
I'm gonna anti this.
Did you hit your head?
Yeah.
Oh, many times. Not just today.
I don't think you can put that thing up.
Yeah, you can. It's just like an X value.
Equals 147. Does my math look okay?
Yeah. Because it's just like it's multiplying on the outside. It's not within the sign.
Yeah. So the next step is to just figure out what that number is. 147 divided by that whole piece of madness there should get you FT1. When you do your math, let me know what you get.
Alright. Radian or degree?
Degree. Folks at home aren't going to be able to see that too well. Let's see.
The answer is 88.
88.
88.3.
332.
We'll go 88.3 then. Newtons. So that's FT1. We already found FT3. So if I want to go ahead and get FT2,
66.422.
that's not what I got. So if I got 88.3 for this, what I could do is I could do a lot of work. I could plug this in for FT1
I thought
here.
you just divided by 1.23. Multiply.
You'd have to multiply, right. And that's where I was going with this. The easiest way to solve
Multiply.
for FT2 is just to use this fact. So if FT1 is 88.3, yeah, 88.3 times 1.33. What's that come to?
117.
Yeah.
I did the opposite thing.
But that's without rounding previously.
Yeah. So then FT2, of course, comes to 117 or so. And that's how that works. Now,
I don't know if you can do this as
depends on how. There was one stoplight. I can't tell you that story now. I got 30 seconds. So I just want to summarize this real quick, but I will tell you about that stoplight. I'll tell you about the stoplight later. This looks complicated, and maybe I lost you, and I'm sorry if I did. But just remember, the main part about this is you're taking all the forces in the x direction, all the forces to the right minus all the forces to the left equals 0. You do the same thing vertically. All the forces up minus all the forces down equals 0. That's all the physics that's here. Everything else is just math. That's the main thing I wanted to say.
Mr. Halfway, did you
Yeah.
say that was the easiest example?
Thank you. We actually did make it through.
Did you say that was the easiest
And the
example?
Nobel Peace Award.
That was the
goes
what?
You said that
to-
was the easiest example?
No, this is not an easy
The one before
example.
that. The one before that.
Which one was the one before this? I don't
Strings and the tattoos and the hanging down.
Oh, yeah.
Yeah, that was the easy one?
Yeah.
Good afternoon, everybody. Welcome to the end of this beautiful day here together at Mark.